try to get started on problem 5. Algebraically independent, that usually means over the complex numbers. It could also be over the rational functions. But so let us assume to the contrary. That's like blue. Vanishes identically, where these are complex constants. And the only idea I got, which I got immediately, that was applying the change of variables with the transformation formulas. And of course we have ek of z plus 1 equals ek of z, and ek of minus 1 divided by z equals minus z to k ek of z. This one gives nothing. That would be very useful if we were working with the rational functions, having a rational function here and then applying this. Then we could reduce the order, so that we reduce it to the complex case. I think I haven't done the details. So let's try to use this guy. This is an M, I'll just correct it. And now what? Well, we could use it to reduce this guy to a polynomial of lower degree, but then we would have monomials as coefficients. Well, I'll try the other way. So let's, instead of this, assume that our polynomials over C, and then we have this one we assume to be the lowest order, and that means that 4m plus 6n as small as possible. Such a guy should exist. And next we choose the maximal order. Let's call this S. Be as small as possible. So first, that the order of the polynomial here in E4 and E6 has a minimal order. That's not well. Sorry about the bad sound. I may have to redo it. This has minimal order, and then we choose coefficients so that the maximal order in Z of this coordinate is minimal. So it's A of Z we have here. Well, first I think I can prove that these have to be constants, but let's look at it. We substitute Z with Z plus 1. And now these polynomials, not all, but for given m and n, they have the same order. And that means that subtracting them gives polynomials of lower order. So if that's impossible, then this must be naught, and that means that all the values displaced in integer are equal, so we have equally many values of the same value occurs infinitely many times, which means that am point n is constant. So if that's the minimum order, then they are all constant. Then we can make this oh, I don't get it. It's not all the polynomials. It's all the polynomials of the maximal order of the polynomial that are constants. If there's any which is not constant, then by doing this trick, we'll get some polynomials, so they'll all have to vanish to get the null polynomial. So it's okay. I'm out of ideas here, so it's time for a break. All right, I don't think I'll do more tonight. It's funny, I got this idea as soon as I read the problem. But I can't make it work. It's about an hour later, and it suddenly occurred to me that I think I did solve the problem. We take algebraic independence over rational functions. That means that these are rational functions. And then using, we assume we have the lowest order possible. And this way we show that it must be a constant then. They must all be constants. The coefficient to the highest order, the polynomial of highest, the monomial of the highest order in the polynomial. And then we use this guy to see that this is also satisfied, and when they equal S, the lowest order, then all the coefficients here are constants, and that means in the original polynomial we can multiply by Z to S and then subtract them. Then we would get a polynomial of lower order. That's impossible, so that means that this polynomial must be the identical Now that's impossible. if they all vanish, then we only have terms of order S here, the order of the polynomial. So we can conclude that we only contain terms where 4m plus 6n equals s. This is the equation we've got, where am point n are complex numbers. So that means, in a sense, it must be a homogeneous polynomial. Well, that was how far I could ride on my idea tonight. Now it's Wednesday, October the 18th, and I've just finished my breakfast, and I think I solved the problem during breakfast. What I did was to look at a concrete example of this relation and we have the I don't know what we shall call it. Well, my idea was to divide by e4 to the 6th. That means that, e6 squared divided by e4 cubed is constant. And then I thought, could that be possible? But that reminded me of the j-invariant. And I just copy the definition. It's formula 228 on page 119. And we can, of course, isolate this guy. Well, we don't need to. We can finish here. If this is a constant, then j must be a constant, and we know it's not. Therefore, no a relation of this kind can exist. That would imply that e6 squared divided by e4 cubed is constant, whatever the relation be. I believe this solves problem 5.